Hi, I want to make a quick video for you and just start the review process. You've had this material before. It's in chapter 1 of our textbook, but you will need to be familiar with it. And so the first thing we want to talk about are functions. Now, if we had a graph in Cartesian coordinates, and if the graph looked like that, that would not be the graph of a function. That is the graph of an equation. It would look something like the graph of x squared minus, let's make that a plus, y minus 3 squared equals 15. Now I just made that up, but it's the right ballpark. So this is an equation, and the equation would have a graph, and it might look something like this. But I can tell with something you learned in grade school, high school, called the vertical line test, that this is not the graph of a function. If I draw a vertical line right here, imagine that that's a straight line. That vertical line cuts the graph twice. It cuts it here, and it cuts it again down here. And anytime you've got a graph and a vertical line will cut up more than once, then it's not a function. It's the graph of an equation. Now, if we took a familiar parabola, maybe a parabola that looks something like this, this can be the x and this can be the y-axis, then that parabola would be in fact the graph of a function, and anywhere in the Cartesian coordinate plane that I drew a vertical line, my vertical line would cut that graph once and only once. This line cuts the graph right here. If you extend it up here to infinity and down here to infinity, it will never cut this line, this curve again. This is the curve that we would call a function. Now, functions have domains, and the domain is the set of values on the horizontal axis that you can, where you can evaluate the function. If we had a function f of x using function notation, and if that function was x squared plus 9, then the domain question is one of what values of x can I put in here that make sense on the right hand side. And the answer is, for any real number x, you can square x and add 9. And so the domain would be the set of all real numbers. We'll use that as a symbol for the real numbers. On the other hand, if we had a function g of x, and if g of x was a function like, and we'll make this just as simple as we can make it, square root of x, then we know that g of 25 would be the square root of 25, would be equal to 5. G of 9 would be the square root of 9, would be 3. So far so good, right? G of negative 4 would be the square root of negative 4. Glad I've got an eraser. The square root of negative 4, and that would equal, well, as a real number, it does not exist. DNE does not exist. So the domain of g of x would be equal to all the positive real numbers. Now, how are we going to write that? Well, we might write that as r plus. Now, actually, 0, you can take the square root of 0. The square root of 0 is 0. So I want 0 in this set, but the positive numbers do not include 0 because 0 is not a signed number. So I would use the union sign and then put my 0 in between curly brackets And in set theory, we read this singleton 0, meaning the set that contains only 0. So here's the domain of G. It's R union 0. Sometimes we might write this domain as 0 plus infinity, and that's acceptable also. When I'm writing, this is called interval notation, and when I'm using interval notation, the square bracket means the value on that end is included. The 0 is part of the domain. The round bracket means that that value is not included. So we've used up about 5-6 minutes here, and I like to try to keep these videos short. So that's maybe enough to get you started. You need to start reading chapter 1, and you need to finish chapter 1 and go to MyOpenMath and do the exercises that I've assigned from MyOpenMath. You need to get that done just as soon as you can. There are due dates you'll see as you look in MyOpenMath, and I'll be with you soon, either on Zoom or on the next video. Thank you. Let's add a second thought to this video before we end it. Let's make a box. We have a sheet of cardboard that's 8 inches by 12 inches, and we'll make a box by cutting pieces out of the corner of the cardboard, like these green lines indicate where we'd cut, and we'll cut squares out. So it'll be X on this side and X on this side, and there would be an X here and an X here that we would cut out, and ditto here, 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 and here. So now we want to know what's the volume of the box we'd form if we would fold the cardboard along these lines. If we do that, we'd wind up with a box that was this dimension right here, this dimension. Let me change color again. Oh, I like this blue. This dimension and this dimension on the base, and then the vertical would be just the X that we folded up. And so what would the dimensions of this box be? Well, the dimensions would be, how much is this? Well, this was 12. From here to here was 12, but we took away X, and then we took away X here also. So the piece that's left would go from here over to here, and wouldn't be 12 anymore, but would be 12 minus 2x. So the first dimension of this box would be 12 minus 2x. Now what about this dimension right here? Well, in the same way, it was 8 from here to here. Now the dimension we're looking at is just from here to here. So that would be 8, but it would be less 2x's. So the second dimension would be 8 minus 2x. And what's the third dimension? The third dimension is how tall the box is, and we can see that's going to be just an x. Now, there are the three dimensions of the box. What's the volume of that box? Let's use function notation and talk about v of x, because clearly the volume of the box depends upon how big or how small we cut this little piece x out to be. So v of x, now what's the volume of a rectangular solid? It's length times width times height, and so it'll be the product of all of these. Now, you, I'm sure, know how to multiply that, but I did it earlier, and I'll just do it for reference right now. 4x cubed minus 40x squared plus 96x. So that is v of x. And if we cut let's see, it's 8 by 12. So if we were to cut, say, 1 inch squares, if these are just 1 inch, then we'd get a box that was just 1 inch high. But the volume of that box would be V of 1 would be equal to 4 times 1 cubed minus 40 times 1 squared plus 96 times 1. Let's see if we can do this arithmetic. So this is going to be 4 minus 40 would be 36, and 36 from 96 would be, if I've got the arithmetic right, would be 60. And if we assume that these were inches, if they were inches to begin with, then this would be inches cubed, 60 inches cubed. All right, so that's one little review and kind of a lesson. But I want to talk about the domain of this function. The domain of the function v of x. And v of x has got really two things that we could call its dimension. We could talk about the math dimension, and the math dimension is just that definition I gave you a few minutes ago. We would look at the function v of x, let's look down here, and say the domain is all the sensible replacements for x. So what values could you put in here and be able to evaluate this, make a sensible expression out of this? Well, it wouldn't matter what x you put in. You could always cube x, multiply it by itself 3 times. You can always square x, and you can always multiply x by 96, and you can do the addition and subtraction. So the math domain would be the real numbers. But besides a math domain, we could have something that I like to refer to as a practical domain. Because as soon as we put some words with a problem like we have right here, we've given that problem a context. And in that context, there may be values of the independent variable x that just don't make sense. Now, what about cutting a little corner off here where x is negative? Well, you can't cut a negative corner off. The smallest thing you could cut, I suppose, would be 0. Don't cut anything. So x could be 0, or it could be a positive number. So the practical domain will not contain any negative values for x. And the practical domain cannot contain all positive values of x either, because if I let x get as big as 4, then what I cut off of this lower section right here would be clear up to here. And what I cut from this upper section would be clear down to here. And I'm going to cut that and throw it away. There's not going to be any dimension on this size because I've thrown everything away. See where this little blue is? That's going to be 0. So there won't be any dimension there. So the domain would have to be the sensible values for x given the context could be 0. I'm using interval notation, comma, so a square bracket because it could be 0, and up to 4, and I'll use a square bracket there also because 4 will make sense, but it's going to give you a volume of 0. These, I would call these degenerate cases, and it's really the values between 0 and 4 that are interesting, but you can defend using 0 and 4 with the square brackets out here, and you may have to defend that at some point. So that's the practical domain. The practical domain is the domain that's imposed once we put a context on a problem. And now this really is enough recording for this first video. So we'll end it here. Thank you for your additional attention.